if I want to make an analogy right now, I feel like tricky Nixon coming after John Kennedy, because I've just come from the field with about 2 hours of sleep from the last 24 hours. I'll show you what I'm doing here. Mostly it's spectroscopy with the French spectroscope LISA and LIRES from Chauliac. There we go. This is a picture of Christian Buell's setup in France. And before we go into spectra, we have to know what is truly light from the star or light from extragalactic object versus light in our atmosphere. And the below spectrum shows numerous sodium lines and also HG lines. We mostly have in Eastern LA, HG lines. In West LA, since they've replaced the infrastructure much more quickly, we have more of the sodium. Here's a spectrum of RS Ophiuchi. That's a symbiotic star in the Ophiuchus. And this shows you can see the oxygen 2 right here. And that's pretty much air glow from aurora-like occurrences in the atmosphere. And mercury. In fact, there's a very sharp mercury line around I think it's 480 nanometers, and around blue-green 5300. Here's my setup. This is what I just put up this morning. Came to LA, took a shower, and came to you all. That's about 1,000 pounds of equipment. The central scope is a classical Cassegrain 13-inch, which is equipped, you can kind of see with the little red camera in the back, LISA spectroscope, which shows the full visual range of 4,000 to 7,000 angstroms. The one on your right is the CDK-17, which I use to take pretty pictures at Pinos, but at home I use it mostly to shoot spectra. And the C11 on that side is mostly for photometry. It has a ST8 with IVB filters. And I typically shoot spectra and IVB at the same time. The Pinos is very good for taking spectra and photometry because it's about 8,300 feet, so it doesn't suffer from much ultraviolet or infrared absorption at the areas of the near-infrared ultraviolet we can see. Here's another example of telluric lines, and this is from Pinos, actually. This is the FO Aquarius star showing, again, the O3 line at 5,900 nanometers, along with H alpha, H beta, H delta, H gamma toward the blue end. Nova and supernova spectrum are very interesting, and they're very persistent. In fact, just last night, I reobserved 2 nova, V5668 Sagittarius, and the other one was Assassin 17HX. One was 1 year old, the other was 2 years old, and they still show very active lines. Here's an example of AT2007 EAW that was in the Fireworks Galaxy NGC 6946. I just put that picture together about 5 days ago at Pinos to show where the supernova is in relation to the stars. North is up there. This is about a 10-hour exposure with the CDK-17 I shot at the end of the sequence of the nova happening. I was able to get 4 months of data, as you see here. It began with just, as you see in the red, a very strong blue signal. And as the nova progressed and the shell came out, the information became more pronounced at the H alpha around 6,560 angstroms, and H beta and H delta absorptions. Okay, this is the first spectroscope I cut my teeth on, the L200, made in the Netherlands by Ken Harrison. He designed it, and it was a really good system to learn high-resolution spectra. 1,800 lines per millimeter grading yielded a resolution of about 5,000. I use the LISA right now from Shellyak to, again, make a whole visual 7,000 to 4,000 nanometer range, and the LIRIS 2 spectroscope to zoom in on that range to give me a typical resolution of about 14,000 at the H-alpha line. And here's an example of a VV Cepheid in H-alpha. This was another symbiotic star, which a very hot B star was going to eclipse around the limb of the red star, and this only happens every 20 years. And it's very informative to take spectra when the small star, the small hot star, is being eclipsed by the giant VV Cepheid star. Just for your information, VV Cepheid is about the size of the solar system up to about Saturn's orbit. It's one of the largest stars known. I think it's about 20, 30 solar masses. This is showing the H-alpha range again. Oops, sorry. And this is the H-beta range, which is a little more noisy because it's attenuated by our atmosphere more than the red H-alpha. Here's interesting facelet of high-resolution spectra, which very few amateurs have tried to accomplish. This is the near ultraviolet around the CAK and the CAH lines. As most spectra at this range for solar-type stars, G stars, F stars, have a dip in CAK and CAH. When there's a flare activity, you typically see a spike in the middle of that shadow range. And it's very hard to see, but there's some little red lines that show a little kind of dot right there. And in the middle of the shadow, you see that spike, and that spike is indicative of X-rays and other far ultraviolet activity going on. And we could just barely get it in CAK and CAH lines. The Solar Analog Project kind of taught me this, that we can, by looking at the near ultraviolet, we can see flare stars, flare activity in stars. Typically, Dr. Gray gave a talk about 2 or 3 years ago about observing solar analogs, and his project involves looking at very, very young stars and seeing what kind of activity they have, because there's a lot of geophysics mysteries of why the Earth didn't freeze when the sun was only outputting about 70% of its energy. So his studies go into the near ultraviolet and the H gamma range. And here's an example of one of the young solar analog stars, HD 222143. It's a G3 type, G3, G4 dwarf, and it shows that big spike in the middle of the CAK and CAH lines. And I depicted the two-dimensional maximum image right there, showing that little tiny spike, which in most stars, in our chromatic calibration stars, there's just a shadow. But in this star, it had activity. It was flaring. And this is the other band he wants us to look at, and it's the H gamma band, about 4,300 angstroms. Now, to get all this working, you need good hardware. Since a spectra is not image you can visualize on your display, you need guide scope of some kind. You know, I use a 200 millimeter Canon lens attached to an ASI 120 monochrome camera that's typically used for planetary. With a 1 second exposure at about 50 degrees Fahrenheit, I can get about 12th magnitude with it. So I can get almost 90% of my variables, symbiotics, or solar analog stars with that. Here's actual two-dimensional image showing how it's an inverse of what the slit looks like on a star. In this case, it's V0883 Monoceros. It's that star that made a beautiful shell, a light echo, a few years ago. And I was taking a spectrum of that. You can see my guide field is very small. It's only less than 6 arc minutes. So if your star was outside the field of view, you would have a hard time finding it and getting data. This is the kind of hardware setup I have on my CDK at home I use. And you can see the LISA spectroscope there. It uses an ATEX 460EX CCD, which is a Sony chip with very little noise. And on the right-hand side, you can see my Canon 200mm lens with the CCD to give me a 3x2 degree field of view. And the other thing you can see on the far right is a little RoboFocus remote power module, which controls my calibration lamps. Before each exposure, I need to take neon argon shots, typically 3 or 4. Before this shot, during the shots, I shoot maybe 7 to 10 images, and then after it, I take more neons and then a flat field. Sequence of about 7 to 10. This is the Lyris, and this, because it can only see a very small fraction of the visual spectrum at a time, usually I look at H alpha. There's a micrometer there on the top, and if I wasn't so lazy, I would go outside and turn it, but I'm lazy, so I put a RoboFocus controller there, and I'm able to control the micrometer reading, so I can stay inside and shoot H alpha, H beta, H gamma, CAK, or CAH lines. Here's a typical neon light calibration lamp with the spectrum of Vega superimposed. In this case, it's H beta. You can see all the lines involved. I use what most Europeans use is the IRIS program, and it can pretty much reduce the spectrum using those calibration lamp lines. Here's a much more busy section showing all the possible lines from 4,000 nanometers to 8,000 nanometers of the neon, which is on the red side, and the argon, which is on the blue side. We usually used argon in the beginning because we only did H alpha. But now that we're doing more work in the blue range, we need argon because there's very little neon in the blue range. Here's a star called Pu Vulpecula. This is a trinary star, and you could see how many lines there are of the star itself, giving practically every Balmer line it can, plus some H from ionized hydrogen, ionized helium, helium-2, helium-3, and a lot of iron. Here's an artist's rendition of Mira with a very bright blue star orbiting it. It's kind of fictitious. The star itself is much further away. It's many, many AUs from the star, so there's not as much interaction as we would thought there would be. Here's a spectra of the Mira system. Mostly it's going toward the red end because most of its data is in the infrared. It's a red star. Most of its data, most of its energy is probably around 8,500 nanometers, 8,500 angstroms, I should say. Here's the interesting part. This is Mira in deep, not deep, but fairly deep for amateurs, ultraviolet, showing spikes here. And at first I thought it was the hot blue companion interacting with Mira, but it's actually the winds between the two stars causing the ionization of H epsilon, H10, and a couple of other deep ultraviolet Balmer lines. Here's another one, called another Symbiotic, called 694 Monoceneros. And it's a system with high stellar winds. There's more activity between the stars. There's more interaction. The dips, the high dips in the visual spectrum above, going from 7,000 to 4,000 nanometers, are indicative of velocity change in the shells of the star. And going to the physical attributes of stars we observe versus the spectrum, this shows an early concept of a shell star seen at various orientations versus how the spectroscopic appearance would be. For instance, the C-type orientation, which is equatorial, would manifest in a star like Pleione, having kind of saddle like this in H alpha. H beta shows pretty much the same thing. These were taken on the same night. These are pretty much the pioneers of amateur spectroscopy. Most of them are in Europe, with occasional mentions in U.S. of Jim Ferreira. I've communicated with all these guys, and they're very informative and very helpful if you have any issues with your spectrum. They would have no problem helping you with that. And that's pretty much it. Any questions? Yeah. Hey. Yeah. Oh, that's a good question. The question was, what size slits do I use on the spectroscopes? What's great about the shellac systems on both low resolution, high resolution, I can exchange slits. Well, I did something. And typically I use 23 micron for the LISA. For the LIRIS, I use larger slits because the efficiency of the light coming in, because it's magnified, is not quite the same. So I use 35. Spectra are very forgiving of light pollution. That's one of the sciences we can actually pursue. I'm about 8 miles from downtown LA, so it can't get much worse. And if I'm at Pinos, if I'm in a remote dark sky location, I could use larger slits without too much of a problem and get more signal to noise. One of the neat things about the ASAVSVO is trying to adopt spectrophotometry. And this has been pioneered by Christian Buell, who we have two slits, like you saw on the shot I showed you of the slit. There's a narrow slit for just spectra, and then there's a full energy slit, which is like 200 microns versus 23 microns. And using both in a reference star, you can pretty much derive BVIR data from spectra without filters, all at once. So it's very powerful, but it's still quite, as far as photometry goes, it may be 3 or 4 times more difficult. So I haven't got to it yet, but I will try to endeavor on that, because then I wouldn't have to use 2 scopes. I can use 1. Any other questions? Yes. 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 That was with ELISA, so that because ELISA is very high efficiency, the resolution was about 1,000 on the ELISA, and I can just about pick up all the data from 7,400 to about 3,900 angstroms. It looks similar to Mira, but it had some more lines in the high-end band, the blue-end band. So we're able to get that in the city, by the way. I shot that in my dark sky site, but I was able to replicate that in the city using the ISIS software. It's pretty good at eliminating most telluric lines, parasitic lines, as French like to call them. So it's a good system if you want to pursue spectra. Yes. Yeah, and they're very, when you look at a normal F or G star and then you look at one of these stars, you know something's weird happening. It's not, you don't want to be around those things. There's high energy wavelengths happening all over, mostly H alpha through H10 and ionized iron. There's a lot of interesting things happening. In fact, the kilonova that was a result of the gravity wave experiment verified that these neutron star collisions are causing high atomic mass products like platinum and iron, beyond iron. Anything else? Yes. Any question? Oh, thank you.